Hello everyone. Today we are going to do an example for beam of how to draw a shear force diagram and bending moment diagram. So in a beam, when you want to draw a shear force diagram and a bending moment diagram, the easiest way is to derive the equation. And sometimes when you have become skilled, understand the loading, like relationship between the loading and the shear force diagram and the bending moment diagram, you don't have to derive um, all the time. You can just look at the loading. You can tell like what will be the shape of the bending moment diagram and the shape of the shear force diagram. But that takes a lot of practice, uh, and also seeing different variety of problem, and it will give you that understanding. So for the beginner, it generally good to just find the equation and then plot it and then draw the final diagram. Okay, so that is what we generally expect by the end of when you graduated uh, in your engineering, civil engineering degree. If you are planning to be a structural engineer, that's the expectation that by the end of the course, you should be able to uh, understand the relationship and draw without doing the equation. Okay, but for now, we'll just see how to derive and then how do we draw that shear force diagram and bending moment diagram from this for this particular beam under given loading. So in this, we have two types of loading. One loading is linearly increasing load because the load is linearly increasing, and then we also have a uniformly distributed load of 2 kilonewton per meter. Okay, so from A to B, we have linearly increasing load with the maximum load at B 3 kilonewton per meter, and then we have a uniformly distributed load from B to C. So the first thing when we're trying to derive the equation is we need to know the support reaction. So here we know that this is our support reaction. We know our coordinate. This is x and this is y. So we have a y and then we have ax and then we have here by. So the first step is to find the support reactions. In order to find a support reaction for this particular problem, we have to convert into a point load or concentrated load, as the given load is here is a distributed load. So in this case, we need to convert them into a point load, and if we convert them into point load, we know that it will always act at the center of mass. So the center of mass of this loading for A to B will be around here. So that will be what we expected. We'll say F1, and then the center of mass for the uniformly distributed load will be exactly at the middle. So we'll say that will be F2. Okay. So the first thing to do is to convert all the loads to concentrated loads. Okay, this is only to find support reaction. Okay, so you will use this concept or this simplification only when you find the support reaction. Do not use it for finding the bending moment diagram or shear force diagram, because it will uh, make your drawing wrong. Okay, so this concept that we convert all the loads to a concentrated load is only to find the support reaction. So if you do that, what you'll find that if you take the whole beam again, A, B here, and C and here, so we have here by, and then we have here ay, and then here we have ax, and if because we have converted the load, that load here will be f1 and the load here will be f2. And the distance between here, we know that for a triangle, the distance of the center of mass from one end, from the farthest end, will be 2/3 of 6, which is equal to 4 feet. And for uniformly distributed, it'll be half of that length. So it will be 1.5, sorry, not feet, meter. Okay, so that distance will be 1.5 meter. And what is F1? So F1 is related to your uh, triangle. So we'll say this is your triangle load, and force. If the load distribution is given to you, the area of the load distribution will be equal to the force. So the area of triangle will be half, and base is 6 meter and height is 3. So that will be 9 kilonewton, and F2 will be the area of a rectangle load, and that will be 3 into 2, which is 6 kilonewton. So that will give you the force from different load distribution, and we have converted all the distribution load into a point load. And now we can knowing all this load, now we can find what is the reaction uy and py. So the first thing we do is we take a summation of your MA about A equal to 0. Remember that moment, if it is counterclockwise is positive, and if it is clockwise is negative. So we're going to see that what are the forces that cause moment at A. So we have F1 that cause moment about A. We are talking about moment about A. So F1 will cause moment about A, because why? Because we have a perpendicular distance. Moment is force into a perpendicular distance or an arm. Okay, so we have F1, which is clockwise, and then we have By, which is will cause another moment, and that moment will be counterclockwise. And then we have F2 that will cause clockwise. So we have three forces that cause moment about A. So in this case, you'll have moment about A, we have By into 6, and that will be counterclockwise positive. And then we have 9 or F1 into 4 feet, and that is clockwise. And then we have F2 into, and for F2 we know that this is 1.5. So basically this whole thing is 9. 9 minus 1.5, or this 1.5 will be equal to 7.5. So that's what we're going to write here, 7.5, and that will be equal to 0. And we already know that F1 is 9 kilonewton, and F2 is 6 kilonewton. So if we write the whole equation again, we have By is equal to 13.5 kilonewton. So that is your reaction at roller support B. And then another equilibrium equation is summation of Fy is equal to 0, and we'll have Ay plus By, because both are upward, so that will be positive, minus F1, because this is downward, minus F2, which is downward, is equal to 0. So here we have Ay, By, F1, F1, and F2. So from here we already know what is F2 is 6, F1 is 9, By is 13.5. So finally we can say that Ay is equal to 1.5 kilonewton. And then we use summation of x equal to 0. You'll find that your Ax is equal to 0. So there's no actual force. Okay. And also here, because you have positive sign, so which means that it agreed to your assumed direction for Ay. What did we assume? We assume it's going up. and we get positive, so that means it agreed to our assumed uh, direction. So here also you can write that it will going upward. Okay. So that's how you find the support reaction for the given beam. And now we are ready to find the derived equation, or to draw a shear force diagram and bending moment diagram. And when we do this, we don't use this problem, or this loading anymore. We'll finally fix on the actual loading. Okay, so please remember that this simplification of the loading is only to find the support reaction. Okay, now once you have the once you have all the support reaction, now you can second step will be to draw SFD and BMD. Okay, to draw the shear force diagram and BMD of your beam, uh, you have to look at first. You have to look at the loading. What type of loading it is? Is it a continuous loading, or is there any concentrated loading or discontinuity? Okay, so here in this case, you'll see that the load is continuous until it hits the support B, and then when it goes to support B, it's from B it's continuous until it hits the end of the beam C. So that means there are two discontinuity. So the discontinuity is here continuous, and then we have this region which is continuous, and then we have this region which is also continuous. So there are two regions of continuity. That means this region is a it act as a discontinuity to your loading. So because of that we have to uh, derive or cut the section between A to B. We'll call it at x1, and then we'll cut this section, we'll call it at for x2. Okay, so we have two equations from A to B and B to C. Okay, so when we cut the section, if we cut the section, then we use for this one to make our life, or to make our equation, or to make our drawing easy. Then we'll say that this is your origin x2, oh sorry, not x2, x1 equal to 0, and this will be till B will be your x1 equal to 6. And then if you cut this section, we see that this section is much complicated. If you take this section here to your left, it's complicated because you have this you have this linearly increasing load, and then you have a UDL. But if you look at the section to your right, if you cut the section, if you look to your right, this is much simpler. It has only uniformly distributed load, and because of that, we are going to say that our origin from for B to C will be, the origin will be around here, x2 will be equal to 0, and here x2 will be equal to 3. Okay, so we'll take a different origin. Does it matter? No, it doesn't matter. You just have to be careful when you take the origin, and you need to know also the limit of your variable x1 and x2. So here we have a variable of your x1 equal to 0, which means that A is our origin, and then we have x1 equal to 6 and B, and that's where it stops your equation. And then we derive another equation for x2. We say that x2 will be origin, x2 equal to 0, and then x2 will be equal to 3, and that will be your limit. Okay, so basically what we are doing is, because we have uh, this continuity in B, so we say that we'll draw SFD and BMD equation from A to B with A as origin, and x1 it belongs to 0 to 6, and then we have SFD and BMD, not B to C but C to B with C as origin, and the limit from x2 will be 0 to 3. Okay, so that's what we are going to do. Okay, so now we'll take from section A to B, which is your x1. Okay, so that means we'll cut the section, we'll take the left side because our origin from here, so we'll take the left side. Okay, you can also take the right side and there's no problem. It's but one of the skill being an engineer is to how can I solve the problem the easiest way or the simple way. Okay, so one of the thing that we have is now if we cut the section, we know that that is AY, and then we have a load here, which is we'll name as W1 for now. And because we cut the section over here, and now this is will be because this is your x value. Remember that this is your x1, and this is x1 is equal to 0. So that means this is your origin. Okay, and now we need to include the direction of the moment and shear force, because when you cut a section in a beam, we have there will be internal reaction, and all those internal reaction are shear force, bending moment, and axial force. But because there is no axial load in this beam, so we ignore the axial uh, reaction. We'll just put only the shear force and the bending moment. Okay, so one of the easiest way to use the direction of the force, shear force, and bending moment is to always consider positive. Okay, the question will be how do we know which one is a positive? We know that if the beam, we're following this sign convention, that if you're applying a beam in this internal moment, or for a beam in a beam, if it bend in this shape, which we call as a sagging shape or a smiley shape, we said that the moment is positive. And then for shear force, if we rotate it clockwise, our shear force will be positive. Okay, so once we have that, now we can put all the direction. So you'll see from here, this is A to X, the section is from A. So if you put exactly the section from A to, for this beam, in this one to find out to put the positive bending moment, so we'll use that as mx1. And similarly, this same length, if we put it here, we'll know that we have to follow this direction of your vx1. Okay, so that is the easiest way to know what is which one to use the direction, and we follow positive sign convention, so we know now the how to use the direction. Okay, so hopefully that will remove all the confusion, which direction should I use. So basically, just if you ever got confused, just draw this and then just look at the section and see which one is it, this section we are talking about or this section. But in the both of this case, we are talking about this two sections, so just draw that direction. Okay, once we have that, and now we need to know what is W1. Okay, so for W1, from here, from the original load distribution, this is length 6 meter, and this is 3 kilonewton per meter. And what we are interested to find is what is this W1, which is at a distance x. For this, we use a similar triangle, if because we see that there is a big triangle with the same origin, and then we have also this small triangle. So basically, we can use similar triangle and similar triangle. That means, say 3, which is your height of the big triangle divided by the length of the big triangle, must be equal to the W1, or the height of a triangle, divided by x1. So in this case, you'll say that W1 is equal to 0.5 x1. So this W1 is equal to 0.5 x1, which is also true. Okay, so W1 at x1 equal to 0 will be 0. So we did see that W1 at x1 is equal to 0, and W1 at x equal to 6 will be 3 kilonewton. So we also see that at 6 will be 3 kilonewton per meter. Okay, so that's how we find all the variable for your um, section AB. Once we have this, then now we can apply the equilibrium equation to find all the shear force and bending moment equation. Okay, so if we take the summation of all the moment about x equal to 0, we'll see that this is about x where you cut the section. You'll see that it'll be ay into 6, sorry, ay into x1. This will be clockwise, so negative, plus, and now for this one, we are considering only this area. Okay, so we know that our force will be around, the force will be acted around here, and the CG of the force will be this distance. So so what we need is the area of your load distribution, which is a triangle, which is half base into height, and the arm or the perpendicular distance, because it is closer to the highest length, so it will be x1 over 3 plus, we remember that we have also a moment applied at the cut section, so that moment also need to be considered, equal to 0. And w1 we already have is 0.5 x1, and ay will be 1.5. So if you put all the value together, you'll see that your mx1 will be equal to 1.5 x1 minus x1 cube divided by 12. So this is your equation, moment equation from A to B. And you'll see that the degree is 3, so it is third degree curve, which basically means that it is a cubic curve. And then if we take a summation of all the forces in y direction, you'll see that this is equal to ay minus vx1 minus half x1 into w1 equal to 0. And w1 we already have is 0.5 x1, and ay is 1.5. So if you put all the value, you'll see that vx1 will be equal to 1.5 minus 0.25 x1 square. Okay, so this is all your equation, and this is second degree curve. So basically what it means that if a shear force is 1 degree, then bending moment curve degree will be plus 1/3. If it is second, it'll be third. It'll be first. It'll be second, and then if it is third, it'll be fourth. So you'll see that it's always 1 degree higher. So this is the basic relationship between shear force diagram and bending moment diagram in terms of the degree relationship, as you'll see too. Also, when you draw the shear force diagram, this is another check to make sure that what you draw is correct. Okay, so that's the relationship in the degree that we found from your shear force and your bending moment diagram. And also we can find the relationship between shear force and the loading also. Okay, so that we'll see at the end. So that's all the equation to derive for bending moment diagram for A to B. Okay, now we are going to go for a section C to B. Okay, the reason I did C to B is because it's easy for me to know that the origin is from C. And if we cut a section, this is a section from C, and we cut a section here, and we know that the origin is here, and this is your origin x equal to 0. Okay, so that's your origin. So now how to draw the moment and shear force direction. So we go again, look again here. Okay, so we say that this is a section that we are interested, and we cut the section over here. So that means the moment here this time will be clockwise, and also for the shear force, we see that we got a section over here, so your shear force will be upward. So that's what we are going to do in here. So the shear force will be upward, Vx2, and the moment will be clockwise, which is mx2. So if you take a moment about x equal to 0, you'll see that this is minus mx2, minus because it is clockwise, and then this is 2 kilonewton per meter, and it is a uniformly distributed, so the area will be 2 into x2, that is your area, and we know that the CG will be half of the length, so that will be half equal to 0, and finally we can find here that mx2 will be equal to minus x2 square. Yeah, so that will be your area, and you'll see that this is a second degree curve, and later on you'll tell you why it is second degree. Okay, so then if you take a force along y direction, you'll get here your vx2 minus 2 x2 is equal to 0, and this is vx2 is equal to 2 x2. Okay, so that is your equation for shear force, and you'll see that this is one first degree curve. Okay, so generally we don't write anymore to the power 1. We already know that if it does not anything, then it should be first degree curve. Okay, so now we got all the equation for your a to b and c to b. So now we can draw the, we know that a, b, c, and a is x1 equal to 0 and x1 is equal to 6, and 2 here x2 is equal to 0 and x2 is equal to 3. Okay. So in doing this, it ensures that we are not making any mistake with your um, variable. Okay. And then I'll also draw the load. Okay, so this is 2 kilonewton per meter and this is 3 kilonewton per meter. This is a 1 degree curve, and this is 0 degree curve. 0 degree curve. Okay, so for the loading, we see that linearly increasing load is 1 degree curve, and for a uniformly distributed load, the degree is 0 degree curve. Okay, now we are going to draw the shear force diagram. Make sure that the lines are aligned. Okay, now that is A, B, and C. And so if you use the equation at x1 is equal to 0, you'll see that Vx1 will be positive, which is 1.5. And then at x1 is equal to 6, your Vx1 will be minus 7.5. Okay, so you see that the value of shear force diagram changes from positive to negative. Okay, so if you have to draw the shear force, then you will say, okay, how do I know that what curve it is? If you look here, you'll see that for Vx, it is a second degree curve or 2 degree curve. Okay, so because it's a 2 degree curve, then means it will, so that is your 2 degree curve. And also you can find that at x equal to here, which if your x1 is equal to 3, you'll find that it should be minus. So if it is minus, that means I need to go back bit, because at x1 is equal to 3, it is minus. So if it is minus, that means it has to be, not, no, that's not right. My hand is shaking. For this reason, that's why I'm not a good architecture. Okay, so that will be 2-degree curve. Okay, and you'll see that at x equal to 3, x1 is equal to 3, your v1 will be minus 0.75. Okay, so uh, so what did you find the relationship here? You'll see that the relationship here is, if it is the load is 1 degree, your shear force degree will be 2 degrees. So you see that the relationship between the load distribution curve and shear force, they always increase by 1 from load to shear force, and then from shear force to bending it increased by 1. So here you have a straight line which is 1 degree, and here you have a curve of 2 degree, and then you will see that now when you draw the bending moment, you should expect a curve of 3 degree. Okay, so and then you'll see that here the curve is 0 degree for the loading. What do we expect for shear force? You'll expect a shear force with plus 1, so 1 degree. So let's see if it's true or not. So you'll see that the shear force diagram for the x2 is 1 degree. So that's the relationship between the load distribution slope and the shear force. So in this case, if you put x2 is equal to 3, you will see, or let's say start from the x2 equal to 0, and x2 equal to 0, your shear force will be equal to 0, and then at x2 is equal to 3, your shear force will be 6. And how do we know, that whether it's a straight line or not? With a straight line of a curve, you have to look uh, at your loading degree curve. If the load is 0, that means it has to be, uh, for shear force, it will be a straight line of 1 degree. So you have here a straight line, and then you just need to draw that. Okay, so now we have all this positive, negative, positive shear force. Okay, so that's about shear force, and now you're going to verify whether everything is correct or not. Okay, so you see that this, you see that for shear force, you see that this shear force is 1.5. What is our AY? Our AY is also 1.5. So that verify your calculation. And then you have by over here, which is 13.5. If you plus the value together, 6 plus 7.5, like this whole length will also be equal to 13.5. So that's how you know that your values are correct, because if you plus them together, your the length of your shear force diagram should be equal to your support reaction. Okay, so that's one. And then another thing is, when I draw the shear force diagram, you see that I draw here slope is equal to 0, which is almost flat. Why? Because at this point the slope of my loading is 0, whereas at this point the slope is the highest. So that's why I have to draw in such a way that the slope will be 0 here, and here will be the highest. And so and that's why I draw here, trying to be a bit slope and then equal to 0. And then here the slope is not the intensity, or the intensity of the loading is not equal to 0. That's why I have to have a slope here for the second part, and the intensity of here of the loading also is not equal to 0. That's why here the slope also is not equal to 0. So the intensity of this load is equal to 0 here. That's why I need to have a slope. Okay, so that's how we check whether your shear force diagram is correct or not. Okay, once we have the shear force diagram, then now we can draw the bending moment diagram. And then for bending moment diagram, just need to make sure that they are in a separate thing. Okay, so for if you put all the equation at x1 is equal to 0, you'll find your moment also will be equal to 0, and at x1 is equal to 6, your moment is equal to minus 9. And if you do at x2 is equal to 0, your moment is 0, and then at x2 is equal to 3, your moment also will be minus 9. So um, mx1 equal to 6, they have to be equal to mx2 equal to 3. Okay, for your x1, x2. Why? Because here you have only the support reaction. If you have only the support reaction and there's no concentrated moment, then what you'll expect is the internal moment will be the same. So if it is the same, then that means your if it is the same, that means your moment also will have to be the same. Okay, now we know that the degree of your shear force is 2 degree, and this is 1 degree curve, and this is 1 degree curve. So we can say that the moment of for this C to B will be 2 degree curve. Is it true? If you look here, it is 2 degree curve. Okay, so even if you put at x2 equal to 0, moment will be 0, and x2 equal to minus 6. Okay, and then what about this? It is 2 degree, then it will be curve will be 1 degree, and now this part is v is equal to 0, or changing from plus to negative, or vice versa. That point will be a point of your peak in your bending moment diagram. So that means it will go up positive, and then that will be your peak, and then it will come down. So you have positive and negative. And this is very important for your FE conceptual. This is your peak 1. Okay, so where do you find the maximum peak? The maximum peak is where the shear force is equal to 0, or the shear force change from plus to negative, and or from plus sign to negative sign. So this is a point that we find the shear force changing from positive to negative. So that will be your peak in your bending moment diagram. Is there any other peak? Yes, there is some. There's one more peak, which is the support. You can see that the shear force changing from negative to positive if you are looking from left to right, or from positive to negative if you are looking from right to left. So this is your peak 2. Okay, so so that's how we know that that's the peak in your bending moment diagram. Okay, and the similar thing also, you'll see that the slope of your bending moment is equal to shear force. So that's why here I have a slope, because I have a shear force, and here also, and then you'll see that the slope here is 0. The slope here is 0 because the shear force is 0, and here I also have a slope because I have a shear force, and this side also I have a slope because I have a shear force, and here you'll see that my slope is 0, close, is almost becoming like a straight line because my shear force at this point also is 0. Okay, so that's the thing you need to know when you draw the bending moment diagram. Okay, and also we already said that positive moment means smiley face, and negative means sad or frown face. So this is uh, so this knowing the bending moment diagram, you can predict what the deflection will be. And this point where the moment is equal to zero or change from positive to negative is called as point of inflection. And what does mean point of inflection? That means it's a point where you change from sagging. If this is sagging and this is hugging. So which means that if I have to draw a if I draw a same beam, how will be my deflection will look? It will look till here, and this is a point of your inflection. Okay, so you have a happy face over here, and then you have a frown face over here. So that will be your deflection, and that point where it's changing from sagging to hugging is your point of inflection. Okay, so I hope this gives you an idea of how to draw the bending moment diagram, how to draw the shear force diagram, how to know that your whether your shear force diagram or bending moment diagram is correct or not. You should look for all the relationship between the loading curve and the shear force degree curve and the shear force with the bending moment diagram. And if you know the bending moment diagram, then you also can uh, conceptually sketch the bending or sorry the deflection of your beam. Okay, so that's all. Thank you.